while your GDC can be used to evaluate definite integrals associated with areas and volumes, it's important that you know how to write the definite integral as part of your working for that. So, when we do the area between two curves, the first one is just dealing with the area between the curve x sine x, which we can't integrate. And that should be your first hint that you should be using your GDC. We don't have a product rule for integration unless it's integration by substitution. And then that would mean that this is the derivative of that, or some form of it. It's not. That's our first curve, and the second curve that we're dealing with is actually the x-axis. Okay, but we don't need to worry about that. What we would need to know to write the definite integral are these points here. And we would get those by going 0 equals x sine x. This is a null factor law, so we'd say that x is 0 or sine of x equals 0. And we want the first time that sine of x is equal to 0, not the second, or the third, or the fourth, because we know that there are an infinite number of x-intercepts, or zeros, for the function sine of x. And this is periodic, so it should repeat. What we do want is the first one, and we know that it's first equal to 0 when x is 0, and then again when x is pi. We've already got x equals 0, so this point here, A, point A, must be pi 0. Okay, so those are our two intercepts, x-intercepts. Why we need those? Well, we want to find the definite integral from 0 to pi and get that area. Because it's all above the x-axis, we don't need the modulus, but I would be inclined to put it in anyway. Just because you remember you're dealing with area. Now, I'm not going to integrate that, we're just going to go straight to the GDC. It's that button there. Integral. We're going from 0 up to pi of x times sine x. I'm just going to type sine because I really don't like that trig menu. My apologies. X times sine of x with respect to x. There we go. Looks remarkably like pi. Okay, so it's approximately 3.14. For the volume of revolution, remember that volume is equal to pi times the integral of y squared dx between the bounds. In this case, the bounds are 0 and pi. So it's pi times the integral of x sine x dx. Make sure you square the function. Alright, so to type that in, pi times the integral (0 to pi). I have no idea what's going on with that. Now, we want the modulus, Actually, modulus is irrelevant, isn't it? Because we're squaring the function. So in brackets, you would type in x times sine of x squared. About 13.8. So modulus not needed here. Sorry about that. Alright, on to another example. This time we're finding the area bounded by two curves. So again, this is a GDC question, and for this one, I would be inclined to go with a graphing page rather than a calculator page. So we add that in, and we've got two functions here. We've got 0.4 times x and we've got, double check that, we've got sine of x. Okay, and the question asks us for the region in quadrant 1 that is bounded by the curves. So the region in quadrant 1, there's only one region here. It's oh, I did not mean to move that. Okay, we can see it there. So we go menu, analyze, bounded area, and we want our lower bound to be there, and our upper bound we can fix it to a point 0.623. In terms of the integral that you would write, well, let's think about it. Once we saw the graph, we noticed, or hopefully you noticed, that sine of x was the top curve. So we're going to go sine of x minus 0.4x. Between, well, 0 is the first one. In order to get this second point, best way to do that is to go menu, analyze, intersection, and tell it the region you want to look for an intersection. There we go, 2.13. And this would be an area is approximately equal to. Alright, let's go back, that was 0.623.